All right, so we have for number one, you had what again? All right, temperature and surface area. And for number two, you had concentration. Everybody good on those two? All right, so I guess that's live at this point because it says end stream. All right, and number three, what happens to evaporation and the amount of water in a liquid vapor system when the temperature is raised? So what happens to the evaporation? It increases. What happens to your amount of water? It decreases. All right, if the temperature is decreased, what happens to the amount of water and the amount of vapor? So what happens to the amount of water if we lower the temperature? And what happens to the amount of vapor? It decreases. Are we okay on those? All right, that's largely what the homework is about, so we should be able to fly through that.
Water increases, vapor, no. Water decreases.
It depends. And the number three, if the temperature goes up, the water will decrease because it'll evaporate. But in number four, we said we lowered the temperature, so the amount of water is going to increase. The vapor will decrease. Now, if you have your 10 openings and you're prepared to turn them in, staple them, put them in the stool. If you're Karen and you've got multiples missing, I guess, yes, give me in a day or two here. You got to give them to me before I hand them back. All right?
Oh, no, I didn't even touch it.
Well, then find your homework so we can go through that real quick. Let's see what kind of questions you have. If any, you might not have any questions. Which would be most fabulous also. Let me find the vapor pressure graph.
I'm not prepared either. Yeah. What was up with it? Oh my God, no, our project? That is ridiculous. That is project? Yes, that is ridiculous.
That's right. You want me to write 6 pages? Like, I know.
Like,
Well, whine about it later and find your homework. Or what, mine? No, they're not. So leave them there instead of stealing them. My guess is that they're probably Mr. Wardlow's and they go in the EC classroom. Exceptional children. Any of you are AIG are also EC, by the way. You're classified as an exceptional child. All right, so if we look at the graph first, since I pulled that one up. All right. Now, all of these are going to be estimates. We're looking at this graph. Okay. So it will not be exact. Okay. The temperature ones should have less of a variation because they're smaller ranges. Questions 4, 5, and 6 will have a larger range because they're just going to have a bigger range because they're bigger numbers. All right. Question 1, I have 36. You should be somewhere in the range of probably about 35 to 38. All right. Are you in that range? All right. That's a little high. You're not going to round to whole numbers. Okay. You're going to estimate somewhere close to where it's at. All right. It's a little harder to do it on a smart board, but they gave you 400 torr. You're going to draw a line over to 400 torr and you're going to read down. All right. You're not at the 40. So don't round up to the 40. Okay. Read wherever it is in the center. You would do the same thing on a quiz or a test. Don't round up to that next number. All right. In B, you're going to come pretty close to the whole number there. So I had around 70. So you might have upper 60s to low 70s, maybe somewhere between 68 and 72. All right. In liquid C, the high 90s, I had around 97. So somewhere probably between 95 and 100. All right. Everybody in that range. All right. Now, when we do pressures are going to vary a whole lot more because when you go from 35 up to the pressures, where's my color? All right. When you go from estimating 35 up to and over, It's just sort of there. Now, some people probably went as low as 350. Some of you might have gone as high as 390. Now, if I look at that, do I think it's close to 400? Okay, I wouldn't put 400. All right, I might have gone as high as maybe 380, but I would probably go 350 to about 380. Anybody in that range?
Yeah.
370 is what I estimated. Okay, but if you went 350, that's okay. I wouldn't go a whole lot lower than 350. Number 5, liquid B. All right, so liquid B would be here. So it's not quite at 200. It's under it. So if you went 200, okay, I think it's under 200. I had about 180. All right, so if you went even 150, I think that's a little low. But if you went somewhere between 150 and 200, I would say you're in the ballpark. All right, and then the last one, liquid C. Liquid C is usually where we have the most discrepancy on this. All right. And that's not quite straight. I'm a little high on that. It should be a little lower. But most people tend to say it's in the mid-range. So what do you pick? 50 is good. All right. If you're in the 50 range, a little higher, 60, 40, somewhere in that range, you're fine. Now, answers 1, 2, and 3 should have what unit on it? Degrees Celsius, and 4, 5, and 6 should say what? Torr. Okay. Now, the next 3 we said were standard. All right. Our normal boiling points. We had to find what yesterday? Standard. All right. Standard pressure. All right. Standard pressure. So what is standard pressure if you have torr? So 760. So again, I'm estimating. So I got to first estimate 760. So I'm just going to estimate there. And I'm going to draw a line across my graph at what looks to be 760. And, you know, you can see I've got a steady rise. So I've already got a discrepancy going on here. All right. So this is my intersection for liquid A. So now I'm going to read down. And I can't draw straight, save my soul. Whew, is that jacked up? Let's try this again. That's a little better. All right, so what do I have for normal boiling point after I draw in standard pressure? I'm in the low 50s, so 51, 52, 53, somewhere in that range. Y'all in that ballpark?
It's because my lines went straight. I got like 55.
Okay, but you drew standard pressure and then read down. Okay, at least you got the process right. All right. So liquid B, something like that. Mine's a little off. I'm a little too high, so mine's probably shifted over a little too far. Mine looks to be about 83-ish there. I'm probably a little lower on my actual paper where I used a ruler. All right. So I have 81 where I used an actual ruler. That looks to be about 83. All right. Are we in that range on B? All right. And the last one, which is going to be off a little more because, like I said, I'm going steadily up on this. Somewhere around 110. Somewhere in that ballpark. Yes? No?
Yeah.
Are we okay on that? On how to draw it? So if I ask anywhere I say normal boiling point, the word normal means you have to find what? Standard pressure. So if I use the word normal tomorrow on the quiz, you have to draw a line at standard pressure. Are we okay with that? Okay. Everybody's okay with doing that? All right. So the last question said, which liquid has the strongest intermolecular force? So which one has the strongest intermolecular force? Nobody has a clue.
I just said A. But it could be C.
All right. The highest boiling point equals the strongest force. So who has the highest boiling point?
C.
That's the answer. Okay. The higher the boiling point, the stronger the force. And that's the answer for anything. It's not just this graph, okay? Anybody who has a higher boiling point has a higher intermolecular force, okay? Questions? You okay on that? Ready to run through the other one? Because this was just like the opening, so this should be pretty quick. Let's see if I got the questions handy. There they are. All right, so question 33. Again, it's a liquid vapor system, and it said to you, suppose we increase the temperature. What will happen if we increase the temperature? So if we increase the temperature, it wants you to answer higher, lower, or same. What will happen to the rate of evaporation? Will the rate of evaporation be higher, lower, or the same? It'll be higher. If we increase the temperature, will condensation be higher, lower, or the same? All right. So if we have some water that is evaporating at a faster rate, because y'all said it was going to evaporate faster, right? All right. So if I evaporate faster, what am I going to make more of? We're going to make more water vapor, right? That's what I get. All right. More vapor. All right. What was the factor that more water vapor increased? Okay. So if we had more vapor, we increased condensation. All right. Are we okay with that? Because we said if we got more water vapor, we increased our condensation. So now go back to the question. If we increase the temperature, what happens to our rate of condensation? It increases. Why will the rate of condensation increase? Because you made more water vapor when evaporation went up. Okay? You couldn't control condensation because you made more what? You made more vapor. If there's more vapor, you automatically get more what? You automatically get more condensation. You can't slow it down. You can't change it. All right? If you evaporate more, you get more what? You get more water vapor. You get more condensation. Those three things happen together. You can't stop it. Are you with me on that? Yes or no? Okay. So what happens to our final amount of vapor? Do we get more vapor or less vapor if we increase the temperature? We got more vapor. So if we got more vapor, what happened to our amount of water? It decreased. We have less water. So is the answer ever going to be the same? No. Nothing can stay the same. All right. So in 34, it wants you to tell them what you would have to do to temperature to get these things. Would you increase the temperature or decrease the temperature? Can you ever leave the temperature the same? No. All right. So if you want the rate of evaporation to go up, you want to increase the rate of evaporation, what do you have to do to temperature? You got to increase it. If you want to increase your vapor molecules, you want more vapor up here, what do you have to do to temperature? Increase it. If you want to increase your rate of condensation, you want more condensation to happen, what do you have to do to temperature? Increase it, because you got to have more what? Got to have more water vapor. And what do you do if you want more water molecules? Decrease the temperature. Everybody with me on that? Okay. All right. Now, are we okay on boiling before I move on to phase diagrams?
Wait, are we okay on what?
Boiling.
Oh, yeah.
It's the last thing we did yesterday. Okay. Now let's talk about phase diagrams. Phase diagrams are pretty easy as long as you learn the parts. Right. A phase diagram is pretty easy as long as you learn the parts. Okay? Phase diagrams show where solids, liquids, and gases exist at a specific temperature and pressure. Now, these look like Y graphs. Just to clarify, because it's easy to get them mixed up, the phase change graph was the stairs. Okay? Now we're going to talk about a phase diagram. And it's going to look like a Y graph. Okay? Completely different graph. You could see both on the exam. You could see neither on the exam. No idea. Okay? I've seen both on release tests, and I have 2 of those. Both of them are 40 questions that I will give you before the review. Okay? They're the most up-to-date release tests I have. One's from 2018, one's from 2013. I'm still debating whether we're going to do a test before the end. I've mapped out to the end of the year. We're going to come pretty doggone close to have covered everything if I skip the test.
Oh yeah,
let's
skip the test.
I'm leaning towards it.
Skip it.
I like
Better exam grade.
I like that.
Probably not.
I didn't say that. All right. Everybody got it?
Wait. I didn't see that last part. The phase change, I better see it. You're right. Yeah, I just like.
Yeah, because it wasn't written on the board.
I swear it is.
You stay in the box.
I'm using Jose's method today.
Are you using what?
Jose's method.
Go right ahead. Seems to be working for him.
I'm done.
All right.
I did not do the graph right there.
Now, don't draw this really tiny. I think I have it the right way. Yesterday I drew it and I had it backwards. I'm pretty sure I have it the right way. All right. These can vary depending on the material that you're looking at. All right. They could be curved. They could just be flat, straight lines. Okay. So it could have more of a curve to it, or it could be very straight. All right. There's no telling which one you will see if you see one. Now, the nice thing about a phase diagram is they always work the same way. This section over here is always a solid. The center of the Y is always the liquid. And underneath the Y is always the gas. That never changes. Okay? Now, there are 4 points you have to be able to find on the graph.
Let me guess.
And we will define those in a second. What?
The middle one? Middle one? No.
Well, one is here, yes. One is up there, and there's 2 others that we have to draw in. Now,
50%.
before we go too far, these lines represent equilibrium.
Oh. The straight ones or the curved ones? It doesn't matter.
Doesn't matter, all of them. Now, this is equilibrium between what 2 states? Yes, dear.
I have a question.
Mhm.
Why did that line stop the curve? Like,
It's just the end. We're going to talk about what that point is in a minute.
okay.
Okay? So, what is taking place on that line? If it's in equilibrium, it's an equilibrium between what 2 states? Okay, it's between solid and a liquid.
Oh my god, craziest thing yesterday.
So what's happening from here to here or here to here?
We were supposed to be Q, and if it wasn't for you, I would have known what it was because it had the equilibrium in it. And we learned that yesterday. Kind of crazy.
It's kind of crazy. Now, what happens when we change from a solid to a liquid or a liquid to a solid? Melting or freezing is what I wanted, but yes, you could go with that too. Okay? So, it melts.
Oh, is that just for this line?
Yeah.
Oh, well.
It melts or freezes across this line. Now, this line down here right here would be in equilibrium also, but what would happen across this line? It's a solid 2A. So what would happen on this line? Sublimation and, I heard it. Give me the whole word. Oh, I got, there we go. There's the rest of the word. All right, you'd have sublimation and deposition. Okay, sublimation and deposition would happen there. Now, so that means on this line, we have equilibrium between what? Liquid and gas. So what happens on this line? Okay, you have boiling point. We'll talk about that in a minute. Evaporation and condensation. That boiling point is one of those points we have to learn to identify. Okay, everybody okay with what the black lines mean in terms of equilibrium? Okay, so anywhere between the solid and liquid, anywhere along that black line where you have a solid to liquid, you have equilibrium between melting and freezing. Anywhere on the black line between liquid and gas, anywhere on that black line, you have equilibrium between liquid and gas, so you evaporate and condense. And anywhere on this black line, you have equilibrium between solid and gas, and so you sublime and depose. Okay? Everybody with me on that?
Yeah.
Okay. Now we need to learn how to identify the 4 points.
Okay, so let's say it's backwards. Like,
Okay.
Like you start the curve like goes from the top down, and the other line is that way. Well, it's like
This one will not be inverted.
Oh, this one.
This will not be inverted.
So
It will not be flipped. It will always look like a Y. Okay? It will not be inverted, sideways, upside down, or any of that. The only thing that would be different is instead of being curved, it will be more straight. So it would be more less Y-ish. I mean, in terms of being curved, it'll just be straight. Okay? And I can't draw very straight. I need a ruler to make it straight. Okay? Well, I could use lines, but so if I went in here and I picked this, what? Yeah, on my desk. So the Y might look more like that instead of the way I drew it. That would be the only way the Y would deviate. Okay? All right, or it could be, it might be. See if I can make this one, more like that. But still, that's going to be a solid liquid gas. The shape of the Y might change, but that's about it.
I would think that those were those angles that you learn in math. You got to find the thing A, B.
No.
Yeah, those absolutely not sucked at those.
No, not at all. All right. Everybody good so far?
I'm peachy.
I'm glad to hear it. All right. So the first point we're going to find is the triple point. And that's the one everybody always remembers how to find, and it's the easiest one. This is the point the solid, the liquid, and the gas all exist at equilibrium.
Okay. Here's 3 points.
No, it's 1 point.
No, I know, but in all.
Yes, there's 4 points in all. Because we're going to do the critical point, the triple point, the normal boiling point, and the normal melting point. So there's actually 4 points. Okay, so it's the point, the solid, liquid, and gas all exist at equilibrium. So to find this one, all right, where do you suppose this one is then? I bet you can even tell me where we find it at. Okay, so it's the middle where what happens? They intersect. Okay, it's the point, the Y intersects. Okay.
That's this.
It's going to be, I'm going to label it on the graph, but yes. So point the Y intersects. Right there, if you want it labeled on that one. I'm moving in a second. I'm just trying to make sure I hadn't forgot anything. Yeah, we're good.
Taking that.
All right, are we there?
Mm-hmm.
All right, so if we go back to the graph, all right, we labeled this just a second ago. All right, here's the point it intersects. So this would be the triple point. Okay, everybody good with that? That's the easiest one to find.
The red is so much brighter on the
I know.
There's having a lot more calm today. Because I worked till 11 last night.
Most of the rest of the week isn't that great.
Where do you work at?
Burger King.
Do you work with Denori or do you work with the other one?
Well, no, he was supposed to get fired yesterday, so.
Oh, yeah, he told me on Saturday or Sunday, whichever day it was raining so much that they told him to park a car and he got written up for insubordination because he said no, he wasn't going outside in the rain.
He said that. He said no yesterday too, and the manager was like, "You just go home. Like, I'm not dealing with you yesterday. Just go home." And so
I was like, wow, dude.
okay, I'm sorry.
I didn't realize it was.
They don't care if it's thundering, lightning, they will pull you forward and give you a free sandwich card.
Yeah.
And you have to wait.
No, I mean,
Over
I was
5
saying that too.
minutes.
Like, I'm not going outside in the rain.
Yeah, I was just appalled. You actually told the manager you were not going out in the rain?
I wish I would do that at Chick-fil-A. I'd get fired.
Denori would not make it at Chick-fil-A. All right, so the next one is the critical point.
Hey.
All right, now the critical point is a little different, and I have no explanation for this, so I just can't explain it.
Wow, awesome.
No, it's that they don't give it one definition. They define it as the critical temperature, and we have another definition for the critical pressure. Why? I don't know. I would love. How on earth did that happen? I just wish I had a reason, and I don't. I don't understand why we just can't call it the critical point and give it one definition.
Okay, so the critical point has two.
The critical point has two separate definitions. Okay, so the critical temperature is defined as the temperature above which a liquid can no longer exist. So once you pass that point, the liquid can no longer exist, and you're going to be a what state? Yeah. You're going to be a gas. Okay? the critical pressure is defined as the lowest possible pressure a liquid can exist at the critical temperature. Now, the only explanation I can give you is they're sort of defined as opposites of each other. All right, so the critical temperature is defined as it can't exist beyond this, and the critical pressure is it can exist up till you get to this. Okay, so less than this, it can't exist, and beyond this, it can't exist. Why we need two different definitions, I just don't have anything. Okay? Seems to me one would be sufficient, but it's not. Does everybody have the top one so I can make it bigger for Caleb?
Yeah.
Okay. All right, so how are we going to find the critical point? All right, so to find the critical point, first of all, it's on the liquid vapor line. And it is the end of the line. It's the ending. Now, I will tell you this. I have seen on some graphs where it'll curve up. You'll see it curve up, and then you'll see it sort of have a broken line like that. If it does that, it's still the end of the graph. Okay? Just stop it where you see that and ignore the dotted broken line. Okay? It's still the end of the graph. Go this way. It's all done now.
Yeah, I know. It could be like 2 more months.
Oh.
What is that?
But it's getting better though, right?
No.
Oh. All right. Some graphs will show a curve and they'll have an end of a graph. Then it'll show like little dotted lines going straight up. If you see something like that, it's still the end of the graph. Wherever that end of that solid line is, that's still the end of the graph. All right. Does everybody have what they want? So we can go back to our normal graph. All right. So if you go back to the graph we drew, whatever graph you have on your paper, this is your liquid. This is your vapor, right? Go to the end of your graph line. Mine is here. So I'm going to draw a dot right there. This is my critical point. Okay? Now, if I want the critical temperature, let me change it back to the other display. All right, if I want the critical temperature, I read down to my x-axis because that's where my temperature is. And if I want the critical pressure, I read over to the y-axis because that's where my pressure is.
And what did you add them together?
Nope, these just be two separate points.
That's
Guess what it is? Everybody with us?
no.
If you want to find the critical temperature, just like in math class, where's temperature out on the graph? Is it on X or Y?
It's on the X.
So you read down to X and find the number,
Okay.
and that'd be the critical temperature. All right? If you want the critical pressure, where's pressure on the graph, Rosanna?
On the Y.
So you'd read over to the y-axis and find whatever number it is, and that would be the critical pressure. It'd just be two separate numbers.
All right, then how did we get the critical point?
The critical point would just be two separate numbers. It's not one number, it's two separate numbers.
Okay.
Okay?
So what about the triple point?
It'd still be two separate numbers. Temperature, critical, triple point temperature, you read down, triple point pressure, you'd read across. It's just like math class, the way you've always learned how to read a graph, even way back in middle school before you truly hated math.
I'm
No, I used to
truly
like
hating
math back then.
Since eighth grade.
Okay, well, this would predate truly hating math because you would have been able to do this before 8th grade. So this would be before you truly hated it. Okay? All right, so the last 2 points are what we learned to do yesterday when we did boiling point. Okay? So we're going to use the words normal, melting point, and freezing point. So what does the word normal mean to us after we reviewed the homework? Okay. Now, so this means at standard pressure. Now, because I said freezing point and melting point, you know it has to be at what line? What? Solid liquid. So we're going to draw a line at standard pressure. And we're going to find the intersection at solid liquid. Okay? Because we want melting point, freezing point. So all we need is that intersection, the solid liquid. Because that's where it melts and freezes at the solid liquid point. Now, the second point that'll be on that same line, because you're drawing it at standard pressure, right? Is the normal, what else? What did we find yesterday? Yep, normal boiling point. Okay, so again, you draw that line at standard pressure, which is already going to be there because I'm going to draw it all the way across my graph. And so where's this intersection going to be at? Gas and who? Yep. Find the intersection at liquid gas. Did you write it down?
Yes.
All of it. Not gonna look up there and go, you wrote more on the board, Miss Wall, I didn't write that. Just asking.
Oh, I can't go to work today. Look.
Okay. That doesn't say normal boiling point, just as a side note.
Wait.
We'll see if you can get somebody else to work for you. Why can't you? Oh. I hate that you're broke. I need to get Shelby a job.
Chick-fil-A's always hiring. Smiling faces.
Not sure she's got a smile on her face from Chick-fil-A.
Did you think I had one? I still don't. Only at
Okay.
work.
Okay.
You think Nakai has one? No, but we just put it on for work. It's a mask. Wait, is that another point? Normal BP?
Yes, which is why I asked if you wrote it down.
Oh, I mean, I wrote it down now, but I thought it was just like extra. I didn't know it.
Yeah.
It's crazy. Are we gonna?
Yeah. No, dear. See all this extra I carry around with me all the time? I'm like a giant polar bear. It's insulation.
It's blubber.
Exactly.
I'm freezing right now.
I don't know what they did to change the heating in here to make it colder, but I just want to send the maintenance people a thank you note. So, this insulation stuff I'm carrying around makes me feel so much better now that they've cooled it down.
Can you identify them?
I'm getting ready to. I was just making sure you wrote it down.
I did.
That's why your classmates are looking at you like, what are you doing that about?
I wrote it.
All right, so find a spot on your graph. I got green dot working. I don't have that up here. Find a spot on your graph. What unit would you like to use for pressure?
Are we doing melting?
Okay, atmospheres is good. I'm going to do both.
No, first, because I gotta do color.
Pick any color you haven't used. I'm using green.
I'm talking through.
I'm talking about you picking a
Oh,
color.
melting point?
Pick a color on your graph that's not been used to draw a line across the
Are we
graph.
doing melting point?
We're doing both at the same time. Draw a line in a color you haven't used. Just pick a color, a line. All right, so since we're using atmospheres, I'm going to put 1 right there so that I have my standard pressure, right? Because we've got to label standard pressure, Annabelle. Which is why I told you to pick a color that you could label standard pressure on your graph. So I'm going to draw standard pressure all the way across my graph. Okay? That's why I said pick a color you hadn't used. Now, you're looking for where the two intersections take place.
Found them.
Okay. Now, the first intersection that takes place right here is across the solid liquid line. So if it intersects the solid liquid line, this would be the what point? Melting point. And what's the opposite of melting point? Freezing point. Okay? Now, the next intersection that takes place, which is here, takes place at the liquid gas line. So that has to be the what? Everybody good with that? All right, we're going to practice briefly, and then we're going to talk kinetics. It should take about 5 minutes or less. Karen, you got this one, right?
Yeah.
It was nice.
Oh, yeah.
Should be nice and easy.
There we go. Thank you.
Okay. All right, answer the 11 real quick.
Is that E or theta?
Where you at? That is an E.
We don't have data in here.
Well, it's a theta.
No, it's an E.
Did.
Not a bad guess, but it's just an E.
Does it hurt? Oh.
Miss Wall,
Yep,
is 6 and 7 supposed to be a number?
6 and 7.
Yes.
Let's see here. 6 says, what was the, yes.
Okay.
Yes.
Maybe not. I'm sorry.
What is it? Remember at the critical point.
Yep. So you're looking for the temperature of that. We done? Need more time? Where we at?
Give me like a minute.
Okay. All right. So if we look at number 1, what section represents a solid?
A.
And a liquid? And a gas?
B.
Okay. What letter represents the triple point?
E.
And the critical point?
E.
E is good. What is the normal melting point?
60 degrees Celsius.
60 degrees Celsius is correct. Okay, we all good on that?
Yes.
Okay, so the normal boiling point would be 100 degrees Celsius. All right, above what temperature is it impossible to liquefy the substance no matter the pressure? 110 is correct. All right, at what temperature and pressure do all three phases coexist? The temperature would be 45 degrees Celsius, and the pressure 0.5 atm.
Wait.
All right, so what point are we talking about for number 9? When it says at what temperature and pressure do all three phases
The
coexist?
temperature was 45.
Yeah, so it would be this. And so the temperature is 45 and the pressure is 0.5. Okay, so are we all good on 1 through 9? All right, so for 10 and 11, since Hallie said that was a struggle. All right, is the density of the solid greater than or less than the density of a liquid?
Greater.
All right, it's greater. This is not anything that's bizarre. All right, and would an increase in the pressure cause the substance to freeze or melt? All right, look at what you've got here. What's happening to the solid section? Is the solid section getting bigger or smaller? It's bigger. So the solid section is growing and the liquid section is doing what? Is decreasing. So as the pressure goes up, the solid section is increasing and the liquid section is decreasing. So what's happening?
Gonna freeze.
It's going to freeze.
I got all these right. Take home this quiz right now.
That's fabulous. Maybe you actually pay attention more when Nakaya's not here for you to talk to.
I don't even talk to Kyle, but she's doing her AP work. I'm just talking to myself. I'm just tired today, so I'm not talking.
All right. Maybe you should be tired more often.
Oh, it's not a fun day.
All right. So kinetics is where we're going next.
And act like you graded it.
You sound like my fourth period class. As well, you're going to collect this after I give them the answers.
You didn't give me the answer for this. I did this by myself and did not change it.
All right.
So,
Fabulous.
you can hold up the
Huh?
separate.
Yeah.
You know,
Take a nap. I don't care. Go to sleep. Go to sleep. I'm not going to wake you up. I don't think there's. It's about the same.
You're on to a lot of
Yeah. Won't matter. Whichever day.
Well,
Both days are all new
can I
stuff.
fit kinetics in this empty space?
No, you can't. All right. So we're going to talk about kinetics and potential energy diagrams with the remaining time that we have in class. Now,
45 minutes of that.
yes. Stop whining. My name's not Bruh. It's not Mrs. Bruh. Now, maybe you should go talk to Miss Pendergrass about that one.
Who? Me?
Mhm.
Absolutely not.
Now,
Miss Well, know what you should do for this class?
what?
You should do what they like do in elementary school and like give everyone a reward of what they were. Like in 5th grade, we did candies. I got the now and later because I'm a question now and later. Jordan Beaster.
I am not that creative.
I think you should. Jordan Beaster got
There's
the
a
red
reason-
hots.
there's a reason I
Got
don't-
mad all the time.
There's a reason I'm not an elementary school teacher.
I think you should do it. I think you should do.
You know, if little kids came up and hugged me, I'd probably just be looking at them like, "What are you doing? And why are you touching me?" Okay,
What
that is
about,
just not my thing.
what about like little paper awards of like what we were to you? Heard.
All right. So during the course of this semester, we've written lots of reactions. All right. Do all the reactions that we've written occur?
No.
No. One of the ways that we used to tell if a reaction would occur was the activity series. Tomorrow and Monday, we're going to talk about a different way to determine if a reaction will or will not occur called Gibbs free energy. All right? And it's going to use the concepts of enthalpy and entropy, which is what we're going to work on tomorrow, which is why I said it really didn't matter if you were absent today or tomorrow. We're still doing new material. Okay? So, before we can do that, though, there are two requirements in order for all reactions to be successful. All right? Which is going to lead us into this discussion of kinetics and collision theory. All right? So, in order for collisions to be successful, all right, what are the requirements for reactions to occur? All right, number one, particles must collide with each other with sufficient energy. Now, this is going to have a name that we're going to learn about in a few minutes, and it's called activation energy. Some reactions do not require a lot of activation energy, and on a graph, they'll have very small humps. Some of you might be morning people, okay? And I'm going to liken the little reactions that have little small humps to those of you who are morning people. Alarm goes off, you get out of bed. It's not a big deal. Some of you are not, okay? And you're going to be the reactions that had big, tall humps. It takes a lot of effort to get out of bed in the morning. You're probably night owls. You don't like to go to bed, and you like to stay up half the night. But in the morning, to get up to come to school, it is your parents or the alarm goes off 4 times. They're in there, get out of bed, you're going to be late. All right? I have one of those children.
My mom's
All right?
gone, dad's asleep.
Now, aside from the fact that you have to have particles that collide with sufficient energy, you also have to have proper orientation.
Which one of your kids, let me guess, is the dude?
So what?
He can't get out of bed.
He cannot get out of bed. All right? They have to have proper orientation.
Do you still wake him up?
Shelby gets up with an alarm. He's had alarm clocks. He's got Google right now. It just plays and plays and plays and rings. Never hears any of it. The fire alarm has gone off. Nothing wakes him up. All right? The house would burn down before he got up.
Do you have to drag him out of bed, literally?
No, I just have to stand over him and yell and shake him.
Shake him.
All right? Proper orientation. All right? They must be lined up correctly. Now, the best example I can give you of that is everybody in here at some point is going to plug in some electrical appliance. And when you went to plug in the plug, did it go in the hole?
Yeah. Yes.
Probably not, because some of them they're lined up for the neutral slot and the hot slot, and the alignment was wrong, and you had to do what to the plug?
Turn it over.
You had to turn it over.
Oh.
Okay? All you had to do was flip it because it had a wider end and a narrower end, and all you had to do was turn it over. Now, if you have a 3-pronged outlet plug that has a round and two rectangular ones, everybody can look at the round one and go, okay, I got to line up the round one with the round hole and the 2 rectangular ones with the rectangular hole. Nobody tries to stick the round one in the rectangular slot. All right? If you do, there's something seriously wrong. Okay? But almost everybody at some point has tried to stick an electrical appliance that had the longer, which is the hot slot, and the neutral slot, and had them not line up, and you had to flip it over and put it in the other way at some point in your life. Okay? Okay, except Kevin, who keeps trying to make it fit. All right? Molecules are the same way. When they collide, are they always going to have enough energy, and are they always going to be lined up properly? No. Out of 1 million collisions, you might only get 100 to 500 that are successful. They collide a lot. Very few are successful because they don't have the correct amount of energy and they don't have the right orientation. Because of that, we are going to talk about what we can do to increase the number of collisions to increase their chances. All right? It's sort of like playing the lottery. If you're going to win the lottery, what do you need to do to increase your chances? A, buy a lottery ticket, and buy what?
A lot of
A lot of them.
I said.
Okay.
I said buy a lot.
I know, you said to buy a lot of them. I said buy a lottery ticket because my husband's always like, we need to win the lottery. I'm like, dude, we got to buy a ticket. All right? We can't win if we don't ever buy a ticket.
You probably have to do it a lot.
Sometimes. Huh?
I said my parents won $12 the other day. They were like, oh, it's okay. They thought it was something.
Yeah, he's forever saying we need to win the lottery. I'm like, we need to buy a ticket. But we don't often buy a ticket. So I don't think we're going to win. It's just a side note. Now,
Invest in it. Stay with it. Andre,
He won the lottery, and then he was like reenacting how he won the lottery and won the lottery again.
all right. So what things can we do to affect the number of collisions we have? All right. There are 5 things we can do to get more collisions.
So there was only 2 for the first question.
Yeah, those are the things that affect the rate. So how can we get more collisions? Can we make the reaction go faster or slower? Let's say faster. All right. What can we do to make it go faster, Hallie? What? I heard it.
Catalyst.
That is not the first one I've ever gotten. I will write it. It is one of the 5, but that is not the first one I've ever gotten. What is a catalyst? That's right. All right. Its sole function is to speed. It speeds up a reaction. That is its sole function.
Bro, I thought a catalyst
Okay.
was a plant. That has something to do with photosynthesis, doesn't it?
What?
A catalyst?
No.
Bring Bowers in here. I know a catalyst is something in biology.
It is. It speeds up a reaction. You probably talked about it with what? Give me an example of a catalyst y'all all talked about in
I
biology.
thought it was like one of them cactus things over
I remember.
That was temperature.
I was thinking it started with an E, an enzyme. All right? Y'all talked about enzymes. Speeds up digestion. Okay? If y'all didn't have enzymes in your stomach, y'all would be really bloated after lunch. But, okay, dude. All right? I was thinking that something else that we always yell out would speed up a reaction.
Nobody yelled it out.
How can we make a reaction go faster?
Not eat it up.
Yes, that's the one that people always yell out first.
What put it in a sentence? Let's eat it up, man.
She always.
All right, so increase the temperature. The particles move faster.
Well, do you think I could do a handstand all the way down that road? Walk down?
All right, so if they move faster, they collide more often. All right, that's usually the one I get first. Catalyst, I usually have to wait on. Okay? That's good. I like that one. No, but that's fabulous that y'all already got that one. Usually we can get 4 of the 5. And you know the 5th one is just y'all don't know how to word it.
Shake it up.
No. We've talked about the other 2. They've been in our discussion the last couple of days. What?
Pressure.
Surface area is one of them. Yes, there's the other 2 I thought we'd get. All right, surface area. All right, so if we increase surface area, we increase collisions. All right, that sort of is an example because some of you are probably like, I don't get it, Ms. Wall. That's like having granulated
Sugar.
Yep.
Yes.
Versus cube sugar.
I'm gonna start finishing your sentences.
All right.
Oh my gosh.
Cube sugar will not dissolve as fast as granulated. Granulated is broken up. A lot of people will use cube sugar like if they're having coffee or tea and they're serving it to a company and they have it sitting out on little plates or trays. Granulated makes a mess if you have it on a spoon and you're scooping it into something. Cubed is much neater to put in a coffee cup or it is. It's just neater. Particularly for people who are messy and you just want to give them a cube to put in their cup.
One time, I almost spilled 100 pounds of sugar.
I don't want sugar.
Because we get these 50-pound bags of them, and I sliced them open, and I was pouring them in there. First one went in fine. The second one, sliced it, the bag fell on it, almost tipped the whole thing over, and it was just not good.
Cube sugar?
No, granulated.
Granulated, yes.
I was like, cube sugar. Where you get
I don't know. I assume they use something that's almost like a gluish type thing, but I have no
For
idea.
what?
Cube sugar. All right,
I'd say
so
they wet it, and then they put it in like huge things, and they have like little cute things, and then they press it. They have wet sugar. It's like no, they just push it down, and then cubes, and then push cubes.
So they put it in a mold or?
Yeah, that's what I would think.
it makes sense. All right, if you increase concentration, there are more particles, so there'll be more collisions. It's sort of like going up the main hall between classes versus now. If you go up the hall between classes, you've increased the concentration of students.
right here. Ink conch.
Increased concentration. Okay, right now, there's a low concentration of students. You are not going to have very many collisions. But if I send you up the main hall at 11:40 when we change classes, what happens during the change of class? All the people are standing in the middle of the hallway. There's a whole bunch of students out there. We've increased the concentration. There's a greater chance that you're going to collide with somebody. I dare say you can't go up the hallway and not run into somebody. All right, number 5, y'all know, y'all just don't know how to word it. Number 5 is the nature of the reactants. And so, for example, give me somebody on the periodic table you know would go fast.
Sodium.
Because it's where?
On
Salt.
the first group.
That's right. So group 1 is more reactive than give me someone who you know would be slower.
Helium.
You both said group 7 or group 18. All right, group 1 is more reactive than group 18 because it's not reactive. Okay? Group 18 doesn't react at all. All right? Now, if you pick something in the transition metals, what have we said about the transition metals? Are they as reactive as group 1? No. Okay? They're much less reactive because we've learned that group 1 is more reactive than which group?
Group 2.
And then group 2 is more reactive than, and then who's less reactive to P? D. Okay? Those kinds of things play into that. All right? Those are the types of things you know under that. All right? Are we okay with that?
Yep. Yes.
Now, how do we represent this graphically? Is where we want to finish the day.
That's a good one.
I don't know, Miss Wall. Why don't you tell us?
I'm going to.
Teachers.
I'm not. I'm just waiting.
Miss Wall, what do you feel about this? So, you know how for like years there's been a class president and a school-wide president, okay?
Okay.
And you've probably been here the longest that I talked to. So, there's like some drama, but not between the students because Maryland's the class president, Mackenzie's the school-wide president, and there was some drama because both of them thought they were giving a speech. Because last year, people got lucky because Blake was the president and the valedictorian. So like they thought that since he was the class president, he was actually doing the valedictorian speech. This year, the people that were presidents only did it to get the speeches, and Maryland did it so she could do the reunions, right? RSGA does nothing because nothing gets approved by Curry. We've tried things, we did Afternoon Buzz, we tried to get music, we tried to do all this stuff. She wouldn't approve it. So the main person that's going to be doing stuff is the class president. But I think, and so does a couple of other teachers that I've been talking to, think because since our SGA doesn't do anything, that there should just be one set of just school-wide reps. So there'd be a school president, vice president, secretary, treasurer, because you have to have those for when you start doing reunions in 20 years. And then there should just be 1 or 2 junior reps, sophomore and freshman, because our SGA can't do anything. Now, if we get a new principal next year, maybe that'll be a little different. Like, I'm tired of Curry declining everything to say, and then there's just drama between the 2 presidents on who gives the speech. Because at first, Mackenzie didn't want to give it, now she does want to give it, and now Maryland doesn't know what to do because she obviously really wants to give a speech. And then, like, Oh, I just think that to cut the drama, cut the BS, there should just be one school-wide president, you know? And they do the reunions and they do that. Wow, this relates to chemistry so much. I had a question for Miss Walker, she's been here the longest.
Right.
Like, what's your opinion on it? Do you think that they'd be smarter or worse?
I think there should be one,
You think?
and I'll leave it at that. I think they should
You agree?
eliminate one set.
Exactly, like,
And this girl doesn't, she doesn't do
All
what she
right.
wants.
and then people have the president and don't do anything about it.
And I'm like thinking I'm missing the meeting, which is happening.
All right, potential energy diagrams is where we're gonna finish. Yeah, potential energy diagrams. PE is potential energy.
Physical education.
Yeah, physical education. Now, we show this graphically in a potential energy diagram. Now, potential energy diagrams can be shown one of two ways. They can either be endothermic or they can be exothermic. Okay, I'm gonna try very hard to draw both before we get out of here. We're gonna start with exo just because I need to pick one. Okay. All right. It's always gonna look like a hump. Alright. It's gonna have a big, like a little roller coaster kind of thing. Now, the y-axis is always either going to say potential energy. It might just say energy. Depends on the author of the graph as to which one they say. Now, the x-axis can vary tremendously. It is always going to say something about a reaction. Now, it could write a reaction, like it could say A plus B becomes C. It could give a real reaction, but it's going to say something about a reaction. It could be more generic and say reactants go to products. Okay? But it's going to have something about the reaction. It could just say course of reaction. It could be even more generic, but it's going to have something about the reaction. Okay? Now, because this graph is illustrating a reaction, the left of the graph is always the reactants. The end of the graph is always the products. Okay? Now, you have to be able to identify things on the graph so that we can identify some things with numbers. I'm going to make this a 0, the top of the graph 40, and the bottom of the graph negative 60. Okay? Now, the first thing we want to be able to find, we said that in order for any reaction to be successful, it had to have sufficient energy, right? Okay. So, activation energy is the first thing we're going to find. It is the minimum energy needed to start a reaction. For some of you, this is the energy to get out of bed. It's your activation energy. We abbreviate it E with a little a. Okay? Energy is always an E. We put a little a there to remind us it's activation energy, but we always use a capital E for energy. Now, to find activation energy, it is always from the reactants to the top of the curve. Okay? It's always from the reactants to the top of the curve. Now, we will also do reverse activation energy. and it has an accent mark on it. So if we want to reverse it, where do we start if we want to reverse the reaction?
The bottom.
That's right, products. So we're going to start at the end. So when we reverse it, we go from the products to the top of the curve. No, that's an accent mark.
Reverse off. Is that what you mean?
Huh?
Accent mark is off.
It's just an accent mark. It just is there to represent it's the reverse activation energy. We have to denote its reverse. So they use an accent mark. Is everybody caught up?
Hold on. No, I am.
If you'd stayed off your phone, we'd been caught up already.
I'm already done. God, just need to see curve.
All right, we there? All right, so we go back to our graph. All right, activation energy has to go from, let me use orange. All right, from the reactants to where?
The products.
No, what did we write? Activation energy goes from the reactants to where?
To the top of the curve.
Top of the curve. All right, the reactants to products is going to be something else. Hold that thought. All right, so the reactants are here. So from the reactants to the top of the curve is EA. Okay, so from the reactants to the top of the curve is activation energy. Now, for the products, for reverse activation energy, all right, where do we start at to do EA reverse?
From products to
Okay.
top curve.
So the products are here. So that is EA reverse. So if I want to find my EA, all right, what does EA start at?
Zero.
Starts at what?
0.
0, and it goes up to the top of the curve, which is at what?
40.
So 40 minus 0 is what?
40.
40. Now, the unit for this that'll be on the sheet is kilojoules over mole.
Kilojoules.
Now, EA reverse. All right. Now, this one's a little harder for some of us, not everybody. It's a number line. What is activation energy reverse?
0 minus no.
40. Negative 60 minus 40.
So what's the total?
Negative 20.
100.
I heard one right answer.
100.
100.
Negative 60 minus 40 is
It's 100.
What?
You go 60,
60.
and then you go another,
40.
so it is 100. Okay? You go from minus 60 to 0, which is 60. From 0 to 40 is 40. So 60 plus 40 is 100. Or you could have done exactly what Annabelle said. 40 minus negative 60 is 100. I just choose to look at it as a number line. You went 100 places on the number line.
Okay.
Something
Alright.
minus and negative.
It's a positive.
Keep,
but
change,
it's not right.
change. Keep the first sign, change the second one, change the other one.
Just add them together and put absolute value.
Okay? Now, the last thing we have to find, for those of you who will be missing tomorrow, we'll use this term. Enthalpy is heat content. Enthalpy. 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 All right? It's heat content.
Sounds like a hippie store.
Okay, dude. It's abbreviated delta H. Alright? Heat content, or delta H. Delta H can be positive, or delta H can be negative. If delta H is positive, it tells us it's endothermic. And if delta H is negative, it means it's exothermic. I'm assuming at this point we should remember that endo means absorbed and exo means release. So I'm only putting those in parentheses in case you forgot. All right? Now, looking at the graph, we're going to figure out which one's which. So, to be able to find this on the graph, all right, this is what Rosanna said just a second ago. Do you remember what you said?
No.
It's from where to where, Rosanna? Do you remember? Yep. This is from the reactants to the products.
Yeah, do it now.
I'm going to enjoy class. Is this your only AP test?
Yep.
No.
Mama. Cause I already took Q and U last year, I'm taking psych next year.
It'll probably be a little bit like fourth period, which is Nori and JD are absent. And they can rush in to tell me, because, whoa, they're absent. And I go, tomorrow will be a little bit like
I didn't hear the first question.
All right, we there?
Yeah.
All right, so if we look here.
Then they wouldn't win.
All right, so if we look at the graph, delta H goes from where to where, first of all? We'll do the easy part. Where do the delta H's start at? At the what to the what? Reactants to the products. All right, so we know delta H is going to start here, and it's going to end here. So that's where delta H goes to. Now, in order to figure out what it is, whether it's positive or negative, we need to figure out, because we're going to do forward and reverse, okay? We need to figure out if it's an endo or exothermic reaction. Think logically. Look at the graph. Is heat released or is heat absorbed? What is it?
I'd say released. It's gone from
Yeah,
negative
we
to
said
positive.
it's
so-
Release because it's
In between 0 and negative.
Why did you say released?
because it's
Don't worry about the negative numbers. Don't worry about what the numbers are. The numbers could be all positive. The numbers could be all negatives or all positives.
It's a bigger.
What's down? What does that mean?
It's lower. Energy's released because lower energy.
Energy's
Energy's going down. No, I don't think it's. I don't know.
Look at the placement of where the reactants and products are in relation to each other.
The product is down.
The reaction.
Which means what?
It's decreased.
It's
So if the reactants are higher than the products, what happened?
Energy is.
it increased and
Right.
it decreased.
Energy is.
You're not giving me what I need.
Okay.
Potential energy, the products and the reaction didn't happen.
The products are lower,
They lost energy.
therefore, 3 dots means therefore, by the way, if you didn't know that.
Really? Why?
Yeah.
Why? Interesting.
It's just an abbreviation, it's always existed. Products are lower, therefore, they, let me make this bigger, Caleb won't be able to see it. It's not what I
It
meant
should
to
be
do.
2 dots or 4 dots, because therefore it's like therefore,
Because you lost
and it
it.
says for, not why for.
Is that what you want?
All right,
Yeah, because heat energy or like?
All right, so products are lower, therefore they lost heat or energy. So it is, yes.
So whenever you have like a little.
So anytime the products are lower, if I go back up so you can see the whole graph. All right, reactants are here, products are there. So anytime the products are lower, you know that it's going to be what kind of graph? Exothermic, which means the products or the reactants gave off whatever heat or energy, so the products are going to be lower in energy. That's what I wanted you to tell me. Now, if the products are higher, what do you know happened? It's being absorbed. They gained energy, which would be endothermic. Okay? Now we want to calculate or assign a number to delta H. Okay? Yeah, we got to find a number. We only said delta H was that blue arrow. Okay?
0 to the negative.
All right, so this reaction was endo or exothermic.
It was exothermic.
So is it going to be positive or negative?
Negative.
So we know delta H is negative. And we went from 0 to 60, so it is negative 60. Now, delta H reverse is the exact same thing, except that it started here and went this way and ended here. So it would be what kind of reaction? Endothermic. So it would be what kind of number? Positive 60. Okay, so the delta H's are the same. The only difference is one's positive and the other one is negative. Will activation energy ever be the same number? No. Will activation energy ever be negative? No. The only thing that can be negative is enthalpy or delta H.
Are we gonna hold one?
Yes, dear.
Why?
Yes, dear.
Your homework is on reading these graphs because the quiz that you have to make up will have these graphs on it.
Wait.
The quiz, the one I was editing earlier had 11, and I haven't decided if I'm going to add more or if I'm going to stick with the 11 I have on it currently.
Or you can just do one of them.
So
I haven't decided.
what
So-
would our answer be? That thing. Yeah.
Kilojoules per mole is the unit.
Yeah, but is it 60 or negative 60?
If I ask for delta H, it would be negative 60. If I ask for delta H reverse, it would be positive 60.
So for
Okay.
activation energy and delta H, the unit is kJ.
It'll be kJ over moles. They're all are the same thing.
So is the quiz gonna be on what we've been doing or everything up until today?
Everything up until today would be fair game. All right, stupid, hit the right button. All right, so if I draw one that's endothermic, just so you have one,
So this is X, that was X.
that was exo. All right, so to draw one that's endo, it would look like that. See the difference?
Yeah.
The only difference is
The reactant.
the reactants are here and the products are here. This is endo. Okay, how do you know it's endo?
The reactant is below the product.
That's right. This is endo because the products are higher. Okay, so if I made up some numbers this time to put in it, and I said 10, 30, and 70. All right, and we want to find all four of them. EA reverse, delta H, and delta H reverse. And potential energy is in kilojoules per mole. So you have the unit. All right, how do I find activation energy? What do I go to? From where to where?
To the reactant.
From the reactants to where?
The top of the curve.
Okay, so I go from 10 to what? Okay, so 70 minus 10 is what? 60 kilojoules per mole. I'm out of space to write. Is everybody okay on that?
Yes.
From the reactants to the top of the curve? Yes, no?
Yes.
Okay, so let me change colors. All right, what would I do to find reverse EA? From the product to, all right, so what's the product? No, 30. I'm at 30 there. Well, that's why I put the numbers in. Don't try to estimate, just go with the numbers that are there. The homework numbers that are on the graph, do the same thing. Don't try to estimate, just go with what number is there.
I thought 20, that's why I put 20 there.
Oh, that's a 30. All right, so 70 minus 30 is 40. All right. All right, last one, delta H. So we got to do forward and reverse. All right, so if we go to find delta H, we go from where to where? All right, products to reactants, I heard up front. So products to reactants, we go from what to what? 30 minus 10. So 30 minus 10 is 20. Is it positive or negative? Is this endo or exo? Endo. Is endo positive or negative? So it's positive 20. So what does that tell us about delta H? It's negative 20. Everybody feel okay about it? And it's kilojoules per mole for the unit. I just don't have any space to write. What'd you say? I just am putting it to show. You don't have to write the plus. I'm just emphasizing. All right.
We have to put the unit.
Do you have to put the unit? Yes. I just ran out of space. I'll make you my able-bodied helper. Do you have this?
Yeah.
It's nuts.
That was.
I'll tell you which ones we're doing on the graph in just a second. You want me to put this up front on your look up there? All right. On the graph paper, you hurry up, take a long perspective. On the graph paper, you're doing the front side. You're just doing the 3 graphs on the front. You do not have to do the 2 on the back. Okay, you are only doing the 3 graphs on the front. Did everybody hear me say it?
Yes.
Here, I'll circle the 3 for a longer.
So this is.
The 3 graphs on the front. The multiple choice, you're just answering 1 through 13. I don't think it's going to tax you to answer 13 questions. Too bad, do it anyway. All right. If you need to do makeup work, I will be here this afternoon. You will need to get the answers